Alrighty then, looks like it's time to get started. Yeah, welcome back everyone. Sorry for the chaotic mess this last week has been. I'm starting to feel better from COVID. I'm still a little out of it to be honest, so I might make some silly mistakes today or be a little bit a little bit zoned out. So you'll have to forgive me for that. So first of all, I want to make sure everything went okay with the substitutes. So you all managed to finish chapter 1 and get through 2.5. Is that correct? Is that about as far as people have gone? Okay. All right. Just wanted to make sure that that's where everyone's at here. All right. Wonderful. And then everyone saw my announcement about the revised schedule and the homework and everything like that. Well, all right. I guess you would have had to see that in order to be at the Zoom meeting. So I'm gonna I'm gonna take for granted that you've seen that. Does anyone have any questions about the revised schedule or how the course is going to work going forward? Feel free to ask over either the voice chat or over the type chat. You can use whichever one you want. If you have any questions? All right, no one has any questions on that. When is the next test? Is the midterm still Friday? Yes. So there will be a midterm this Friday. It'll essentially be like like a longer version of the quiz that you had the week before last. So it'll be like a few kind of just short questions, except there'll be a few more of them because you're going to have the whole period to do things. By the way, so I didn't actually consult with the sub on that Thursday. How was the time for that quiz? Did everyone feel like they had enough time to do that, or was it too long? What was the general consensus on how long that quiz was? Did you think that you had enough time to do everything? Okay, we got some yeses. If you don't feel like it was and you don't really feel like putting that in the chat, just send me an email being like, oh no, I definitely didn't have enough time. I finished in 3 to 4 minutes. Okay. All right. Okay, good. So I'll keep that in, not the 3 to 4 minutes part, but I'll keep into account you have enough time when I'm writing the exam here. And these aren't supposed to be long. It's more just to see if you understand what's going on. I'll return your graded quizzes to you on Wednesday, if we hopefully meet in person. All right, so that's good. So yeah, there will be an exam this Friday, and on Thursday, we're going to have some review in class. In addition to learning some new material, we're also going to review in class. So I'll maybe go over a few types of problems that could be on the exam and kind of go over the content and also talk about just studying. All right, anyways, so that's all of that information. So hopefully everything uh, is clear from that. Which quiz are we talking about? The only quiz we've had so far, the one that we had on the first week of class, quiz number 1. All right, anyways, so let's go ahead and get started with today's material. So I kind of want to give my own introduction to chapter 2 because I missed it. So chapter 1 had to do with the sets part of sets and logic, and then 2 has to do with the logic part of sets and logic. Now, sets may be something you're not really familiar with working before you came to this class, but I'm assuming that everyone has some amount of logical capabilities. I mean, you kind of need that to function as a basic human. So that kind of begs the question, why are we even bothering with that? Like, I understand how logic works. Like I'm a logical person. Why do we need to spend time talking about logic formally? And the answer is that sort of like sets where things work out the way you'd expect most of the time, but there could be sometimes some instances where things can get a little bit confusing if you're not careful. So kind of like how there was a Russell's paradox with sets, there can be some sort of confusing instances or unclear instances with logic as well. So it's best to be rigorous and careful when you're going through logical statements. Now, granted, you're not going to need to come back to truth tables and the core of logic every time you do mathematics. Mathematics happens above that level. kind of like if you're computer programming, you don't need to go to assembly language every time you write a program, but it is good to be at least somewhat aware of what's going on under the hood. So that's the purpose of this chapter. So hopefully at this point you've talked about what a statement is and what an open sentence is. So a statement is something that's either true or false. And an open sentence is something that could be true or false depending on some sort of variable. And then you hopefully talked about also the conjunctions and, or, not, if then, and if and only. I think that gets us up to section 2. All right, so let's go ahead and start on some new material here. And of course, if you have any questions on the older material, feel free to send me an email and or ask me after class. I'd be definitely able to help you with that. Also, another thing I forgot to mention in my announcement with office hours. So I'm going to have office hours at different times this week. And then starting next week when we're in person, I'm going to move them permanently to a different time. And I'll send out that information in an email. So that'll be for office hours. Anyways, let's go ahead and talk about today's new materials, logical equivalence. So when we were learning about implication, or if the statement P is true, then the statement Q is true, or if P, then Q, the substitute may have told you that this statement is actually the same thing as saying not P or Q. So this is another way of thinking of if P then Q. Actually, the if is a bit redundant here. We really just have P implies Q like that. So this statement right here means exactly the same thing that this does logically. And so these are said to be what are known as logically equivalent statements. Okay, so what does logically equivalent mean? Logically equivalent is saying that when we have a logically equivalent statement, their truth values match up line for line on a truth table. So if we were to write down a truth table involving P and Q, and then these two combinations of P and Q right here, then this one would be true all of the same times that this one would be, and then this one would be false all of the same times that this one would be, and vice versa. And so logically equivalent is kind of a fancy way of saying that two statements mean exactly the same thing. They're saying exactly the same thing in terms of truth or falsehood. So let's go ahead and see why these two are logically equivalent, and we can go by the definition here. All we need to do is draw up a truth table for P implies Q and not P or Q, and we just see if they have exactly the same column in the truth table. Let's go ahead and do that. Let's go ahead and practice here. Get some more practice with our truth tables. Hopefully you've been practicing that the past few lessons here. So we have a column for P, we have a column for Q, and then we have the two statements that we're interested in. So we have P implies Q, and then we have not P or Q. All right. By the way, hopefully the substitute explained to you that it actually is important to have the parentheses here. Why do we need to, can someone say in the chat maybe why we need to have parentheses around this not P here? What would happen if we didn't have that? That's right. Very good, Malik. So yeah, so this could be mistaken for the different statement, not logically equivalent, not P or Q. So it's unclear if you just put the not in front of this whole thing without a parenthesis, whether the not's going on this P specifically, or if it's going on the whole statement. So that's why I'm making a point of putting these parentheses right there. And I strongly encourage you to do the same to avoid ambiguity. All right. So anyways, let's go over the truth tables here. So remember, the number of statement variables we have in here, which is 2, because we have P and Q, you're going to have 2 raised to that number of rows in your truth table. So since we have 2 different possibilities for our statements, P and Q, and each one of those can either be true or false, that's going to be 2 to the second power, or 4 different rows. So we have all of the instances where P is true, false, and then all of the instances where Q is true or false. And so here we have all 4 of the different possible combinations. All right. So then what we're going to do is we're going to fill out this table, and we're going to see that since these are logically equivalent statements, they're saying literally the same thing, they're going to have exactly the same column on the truth table. All right, so let's go through the P implies Q column. So remember, an implication, I don't know how they explain it to you when the sub was here, but an implication is like a promise. The implication is saying that whenever we do have P being true, it'll also be the case that Q is true as well. That's what the implication is. So if we have P being true and Q being true, well, then that promise is fulfilled. So that will be true. However, if P is true and Q is false, then we failed to uphold that promise, because we're supposed to have this being true whenever that is. So this will be false. And then these 2 instances, and this is a little bit weird, I don't know if you discussed this with your substitute or not, but when this is false, then that doesn't really concern the promise we made here with the implication. Because the promise we made with this implication is that whenever P is true, something will happen. So it doesn't really say anything at all when it's false, or rather it's not breaking the promise. So these are said to be true whenever P is false, regardless of if Q is true or false. And this is kind of one of the weird things I was mentioning earlier about logic that is kind of hidden behind the scenes here, are these 2 truths right here. All right, and then let's go ahead and go through the truth table for not P or Q. So that means that one of these statements, at least one of them, or both of them, needs to be true for this to work. All right, so let's see. So since Q is true here, well, we automatically know that's going to work regardless of whatever that is. Q is false here. All right, so we have to hope that not P is going to be true, but not P in this instance is false. So both of these would be false, meaning that the whole thing is false. And then finally, here we have Q being true, so that's enough to make this whole thing true. And then we have not P being true, and that's enough to make the whole thing true. And we see right here, once we've completed our truth table, that both columns are identical. So that means that these 2 statements, P implies Q and not P or Q, are logically equivalent. Now, they don't really talk about this in the book, but I just kind of want to mention this just for your own background knowledge. So there's logical equivalence, and then there's also something called material equivalence as well. You talk about that if you formally study logic. So materially equivalent is saying something like, today is a weekend, or a day is a weekend, or a day is Saturday or Sunday. So those 2 statements are the same, they're equivalent, but those would be said to be materially equivalent because it more relies on our knowledge of what a weekend is or what the days of the week are, rather than any kind of pure logic. Like we didn't write a truth table to see that that was true, for example. So that would be an example of material equivalence. And this is an example of logical equivalence. It didn't really matter what the context is for these statements. This is going to be true no matter what. I just wanted to bring that out there because that's just something to be aware of, I suppose. All right, but we're not going to mention that again. I just wanted to throw it out there. All right, let's go ahead and look at another example of this. Here's another example. So P, if and only if Q, is logically equivalent to the statement P and Q, or not P and not Q. All right. Let's take a minute and look at this one and see if these 2 statements really are logically equivalent. We have P, Q, And then we have P if and only if Q. And then sometimes the statements here can get a little bit complicated. We have these compound statements right here. So sometimes it helps to break them into pieces. So I'm going to have a column for P and Q. I don't need the parenthesis there. And then I'm going to have not P and not Q right here. And then I'm going to have the final statement here. So you don't have to do it all at once, although you certainly are welcome to. But sometimes it helps to kind of break it into pieces like this. All right, and remember, we're trying to see the logical equivalence of this statement right here and this one back here. We don't really care what these intermediate ones are doing. This is kind of just like our scratch work. We really care that this column right here is exactly the same. All right, so once again, we have 4 different possibilities for the truth and falsehood of P and Q. Okay, now could someone maybe in the chat or verbally say what the truth values will be starting at the top going downwards? What will be the order of these here for P if and only? That's right. Very good. So it's going to be true, false, false, true. And loosely speaking, P if and only if Q means that P and Q share the same truth value. So they're both true here, meaning that this is true. They're both false here, meaning that this is true. But then if they have different truth values, then we can't say that this is the case. All right, now let's go ahead and see if this ends up being the same as this right here. Verbally, I pretty much did just say this. So you either have P and Q both being true, or you have B and Q both being false. So intuitively, we see that this will be the same, but let's go ahead and verify it. So P and Q, so this is only going to be true here and false for all of the rest of the times. And then we have not P and not Q here. So I guess that will only be true when these are both false, because then these will both be true here. We have true, and then all of these will be false. And then finally, we do or of both of these columns right here. So true or false, that gives a true. False or false gives a false. False or false gives the same thing again. And then false or true gives true. And we see that these statements are going to be logically. All right, I think everyone understands the point of this now. 2 statements are logically equivalent if you can produce a truth table that gives them exactly the same column. So what I'm going to do now is I'm going to list out a bunch of logical equivalences that will be useful for us as we're going to begin proving things starting in chapter 4. I'm going to write out a few logical equivalences, and I'm not going to write out the truth tables for these. I'm just going to state them. So here's one right here. Actually, I'm going to write 2 of them. They kind of come in a set. So we have not P and Q is the same as not P or not Q. And then we have it, but with the and ors flipped. So we have not P or Q is logically equivalent to not P and not Q right here. And these 2 logical equivalences actually have a special name. Has anyone ever heard of the name of these? Does anyone know the name of this? Any chance? That's right. Yeah. So it's good. These are what are known as DeMorgans laws. And what they're saying here is if you're not P and Q, then you either need to have P be false or you need to have Q be false. And if you're not an or, well, then that means you need to have both of these be false. You need not P and not Q. So this is pretty much just explaining how to negate an and or an or statement. That's what DeMorgans Laws do. All right, so we have those. Here's something I hope that they taught you while I was gone. So P implies Q is logically equivalent to not Q implies not P. And when we flip the order of an implication and we negate each of the individual statements, this is called finding the contrapositive. And a statement is always equivalent to its contrapositive. So if you want to show that P implies Q is true, it may actually be best to show that not Q implies not P. So that's actually a legitimate mathematical strategy that we use on many instances. We'll see that in a future chapter. This is the contrapositive logical equivalence. We have P and Q is the same as Q and P. And then the same thing goes with or as well. There we go. Does anyone, we've talked about the word that represents when we could flip the order and it remains the same. What word did we use for that? Does anyone remember? Commutative, very good. So this says that and or are commutative. So these are logically equivalent here. So these are commutative. All right. Now I think someone pointed this out in a question, or maybe I was just chatting with someone. They pointed out that the intersection and union have a distributive law, and that ends up being true. And additionally, and or also have a distributive law as well. So it turns out that P and Q or R is the same thing as P and Q or P and R. Sometimes I always do this. Sometimes I just write an A because I'm thinking and when I write this. That's going to be a mistake I do. So sorry about that. I didn't mean to put the line through there. And then we also have them if we flip the and or. So P or Q and R is the same thing as P or Q and P or R, like that. And what's it called when we can take this and apply it to both of the things in here separately? That also has a name. What was the name we used for that? Very good, it's distributive. All right. And then finally, one thing that we kind of take for granted, but is certainly true, is P or Q or R is the same as P or Q or R. And then the same works with ands as well. P and Q and R, like that. And there's one more fancy word that goes with these. What was the terminology representing you can evaluate the pairs in different orders? Associative, that's right. So everything I wrote down, these are all logical equivalences, and it doesn't matter what statements P and Q we use. We could be talking about literally anything, mathematical or not. All of these statements will be logically equivalent. So they mean the same thing. And this sort of gives rise to it, like you can think of it almost as like an algebra, but for logic. So these are sort of like the algebraic rules for how we manipulate logical symbols. Okay, now some things to be aware of. So if you have a logical equivalence, they have the same truth table, but there are some times where we have logically inequivalent. So for example, let's take a look at P and, oh God, I did it again. I'm going to do it so many times. P and Q or R is equal to P and Q or R. So this almost seems like an associativity, but we do it when we have a mixture between the and or. So are these two going to be logically equivalent? Is this going to work out? Will something go wrong with this? Yeah, that's right. Yeah, there's going to be an issue with this one. So we could see that two statements are not logically equivalent when they have different values in the columns of their truth tables. So let's practice writing this one right here. And this will also give us practice writing a truth table that has three different statements for inputs here. We have P, Q, and R as possible inputs into here. So we have P and Q or R, and we have P and Q or R. Okay, so if these really aren't saying the same thing, then there should be some differences in their truth table here. Now let's see how we're going to set up a truth table with 3 different values. Hopefully you covered this, so hopefully this is just review. So how many rows should we have in this truth table? That's right, Sam. Yeah, so 2 cubed will be 8 because there's 2 possibilities for each one of these right here. All right. So the way we write this out is for the first one, we put half of them being true and the other half being false. For the second one, we do sets of 2, true, true, false, false, true, true, false, false. And then for the final one, we alternate every time. True, false, true, false, true, false, false. And when we did that, we have all 8 possible combinations. All right, so then let's go ahead and fill in these tables here and see where they differ. And they're actually the same for quite a few of them, but there will be some instances where they're different. All right, so let's start filling in the table here. So we have P and Q, which is true, or R, which is true. In fact, anything that has an R being true, this will automatically be true because this is an OR. So this is true, that's true, and that's true. So we could fill those in right away because we know that R being true automatically makes this true. Now for the ones where R is false, we need this to be true to pick up the slack. So in this case, we do have that because P and Q is true in this instance. So we do have true there. But then we have R being false here and P and Q being false. So there's no truth to be had in this OR. So that's going to be false. And then the same with the rest of them, because in all of these instances, P and Q will be false. All right, so there we go. We filled out the truth column for P and Q or R. Now let's do P and Q or R. All right, so the and is very strict right here, right? And is harder to satisfy. So anyone where we have P being false, this will automatically be false because we need P to be true for this to work. So we know that down here, all of these will be false. And this is where we can start to see our differences here. So in this row, we have an F here, but it would actually be true here. And here we have an F there, and then this would be true right here. All right. And then now, in the instances where P is true, we need Q or R to be true. Now, it's going to happen here, it's going to happen here, it's going to happen here, but Q or R is not true for this one. So it's going to be false here, but then we do have it being true for all of these up here. So it turns out that 1/4 of these instances will cause these statements to differ. So this row, they definitely have different truth values, and then this row as well. All right, so these are not logically equivalent statements. So you can come up with instances where they would be different. All right, and that's all about it for logically equivalent. Does anyone have any questions on what we've done so far? All right, let's move on to the next section. So 2.7. 2.7 is going to talk about what are known as quantifiers. All right. So hopefully you've been introduced to the concept of an open sentence, which you can think of as a statement that depends on some sort of variable x. So for some x values, the statement P of x may be true. For others, P of x will be false. Okay, now let's suppose that you wanted to make the following statement. Every n that is an integer or contained in the set Z here is odd. Let's suppose we have this statement right here. And by the way, is this statement true or false? Yeah, that's definitely false. Yeah. Yeah, so every whole number is not odd. Like 2 is a counterexample. By the way, this is just a false statement. Well, let's say we were considering this statement anyway, even though it is false. So the way we could write this symbolically using ands or ors is by defining the open sentence O of x to mean the number x is odd. So this will return true if you put an odd number in here, and it will be false if you put an even number in here, or a not odd number. All right. So this statement right here would be equivalent to O of 0 and O of 1 and O of -1 and O of 2 and O of -2 and so on. And notice that we didn't need the parentheses here, because remember, the and operation in logic is associative. So it doesn't matter which pairs of these we combine first. However, this does seem to go on forever because, well, there are infinitely many integers to go through. So this kind of poses a problem when we want to put this in symbolic terms. We have this sort of infinite conjunction of these statements here. And one way we could get around this is we could adopt notation similar to the way that we did the intersection back in the sets section. So there actually is a notation for infinitely many ands, and you can write it as a big and symbol, then do I equals 1 to infinity like that. And you could actually write this statement in that fashion if you want to. However, despite the fact that you can do this, this actually isn't what's commonly done in mathematics. There's actually a different way of writing this statement that doesn't use that notation. Rather than writing something like this, we would instead say that for all n contained in the integers, we have that n is going to be even, or O of n. They may be like, okay, oh, Dr. Manley, you're still sick. You wrote your capital A upside down right here. So it turns out that this is actually a special symbol, and this is called a universal quantifier. And what this means is this means one of the following things: for all, or for each, or for every. So it's effectively a compact notation symbolically expressing these phrases here. So let's reread the sentence here now, knowing that. So when we see this upside down capital A, we see that this is saying for all integers n, right here, or for all n contained in the set of integers, we know that this statement is true, O of n, or that the number n is odd. So that's a compact way of writing the statement, and we also don't need to use anything like this here, which really isn't that common in the logic. So that's called a universal quantifier, and that's saying that all of the members of this set are going to satisfy the statement that follows here. For O of x, we don't need to specify that n is an integer because of the quantifier, right? Yeah, we didn't need to specify that here because we could also have a context. Maybe we're looking at something different right here. So maybe we're looking, oh, maybe a real number could be odd. So we didn't actually need to specify that right here. And because we already said that we were talking about integers. All right. So this statement is certainly false. However, what if we wanted to change this up and make this be an actual correct statement instead? Well, one thing we could do, one way we could change this to make this a correct statement, is that there is an n contained in Z that is odd. So rather than saying, like this first statement, that every integer is odd, this new statement, which is not the same, is saying that there is an odd number out there. So if you look in the sea of all the integers there, there's going to be an odd number. Is that true? Is there at least one odd number out there in the whole numbers? Yeah, that's definitely going to be true. Yeah, probably. Yeah, yeah, you're pretty likely to find one. Yeah, so we can come up with examples, of course. There's like 1, 3, negative 101, whatever like that. So this is actually going to be a true statement. But the truth or falsehood really isn't what we're concerned about for this statement here. We want a compact way of expressing this in terms of symbols. Now, since this one used every single integer needed to satisfy this property. So we had all of these ands connecting this. So in this case, there just being one of them means we would connect all of these with ors. So we need to have 0 being an odd number, or 1 being an odd number, or -1 being an odd number, or 2. I keep writing C. Or -2, etc. So all we really need here is at least one of these to be odd, and that will be satisfied by having this infinite chain of ors right here. But just like we don't really write down infinite chains of ands in our statements, it's not really common in mathematics to do infinite chains of ors either. But there is a way around this, kind of like we had a compact symbol, meaning the for all, for each, or for every. There's another compact symbol that we use to show that there is something. So the best way, the mathematical way of writing this statement out in symbols would be there exists an n in the integers such that n is odd. And by the way, I'm not sure what notation the substitutes introduced to you, but these colons right here, if you see me write that, that's a symbol meaning such that. And you'll see that fairly often. That's a fairly common standard, but some people just use commas instead. I think that's a little bit worse because you often use commas in the preamble here, so it can be kind of confusing when you're putting your such that, but that is something that people do. All right, so the best way to write this statement in terms of symbols would be there exists an n in the integers such that n is odd. Can you use the vertical bar like with set builder notation? You don't really see that very much, to be honest. I don't really recall reading a lot of texts that would say something like this without the set symbols around them. But I wager that if you wrote that down, people would know what you meant. But it's better to use this if you're talking about building logical statements rather than set builder. And that's just kind of a cultural thing. Like it logically makes sense to also use that here, but culturally you don't really see this very much, or at least I haven't seen that in the mathematics I've read. There are definitely different notations out there, but I don't think this one's nearly as common. All right. Anyways, so let's explain what this symbol right here means. So this is, instead of an upside down A, we're going to use a backwards capital E. We're using a backwards E because of the word exists. So this symbol right here means there is or there exists, meaning you can find at least one out there. All right. And these two quantify, oh yeah, and this, because of the exist part, this is called an existential quantifier. I hope I spelled this right. Sorry, I'm still a little out of it. This is the existential qualifier. And these are really commonly used in mathematics. In fact, most mathematical statements you see will include something like this, either in English or in symbolic form. So it's incredibly crucial for you to understand what these are doing. All right, so let's go ahead and look at some more examples here. All right. So let's take a look at another similar statement. There is an integer that is not even. All right, so let's see how we would write this out using our quantifiers here. All right, so we want to say that there is something. We want to show that something exists. So the way we would begin here is we would put our backwards capital E. So there exists, and we're considering ourselves with integers in this case. So there exists an n contained in the integers. And what's the property we want it to have? Well, we want it to be not even. So what I'm going to do is I'm going to define the open sentence E of x being where x is an even number. And what I'm going to do here, my statement then will be not E of n. So what this is saying is that there exists an n contained in the integers such that there's an integer that's not even. Why did I use the comma for the first but the colon for the second? You'll see either of those written out. So sometimes people use colons, sometimes people use commas. I believe the book mostly uses commas. I'm mostly going to use colons. I feel like me and this author grew up on opposite mathematical traditions pretty much. But you'll see both of them. So I may write a comma instead of this colon. It could be either way. I personally think it's better to use the colon. Not everyone does. All right. So anyways, that's how we would translate this statement using our quantifiers here. Let's take a look at another one. Every integer that is not odd is even. All right. So for this one, we're talking about every integer. So what is that going to say? So we're going to have to use our for all symbol here. So for all n contained in the integers. Now, so that's the setup here. We're talking about all of the integers. We want something to be true for all of them. And then what is the content of the statement? What are we trying to say here? We're trying to say that if you're not odd, then you are even. So we're really talking about an implication here. So what we're saying is that not being odd implies that you will be even. So for every n that is contained in the integers, I'm going to use a comma this time, we're going to say that not O of n implies that you will be E of n. Like that would be how we would translate this one into symbols right here. All right. And notice that these all kind of follow the same pattern here. You kind of begin by determining the context or what you're talking about here. So we usually have some specific set we're talking about. We give a name to one of its members. And then once we're done establishing that, and whether we're talking about there just being one at all, or being true for all of them, then we say the content of our statement next, which actually is kind of similar to set builder notation. It kind of feels the same way. All right. And let's break away from odd and even here, because of course this can be used in any context really. The product of two rational numbers is rational. So what are we saying with this statement? We're saying that if we multiply two fractions together, then we're going to get another fraction, or possibly an integer, which we can imagine as a fraction divided by 1. All right, so how would we express this in symbols here? Well, in this case, we're actually talking about two different rational numbers, or at least potentially different rational numbers. We should probably have different names representing them. And one common thing you can do here is you could just list the two names. So I'm going to call them A and B. And then I'm just going to say that both of these are in the set we're talking about, which is the rational numbers. So sometimes we use multiple for alls. And this is actually the same as saying for all A contained in Q, and then for all B contained in Q. So these two things are actually saying the same thing. So for brevity, we usually pick this one right here. So we're saying that for any two rational numbers A and B, now what's the content of our statement here? For any two rational numbers A and B, we want the product of them to be rational as well. So the product means the result of multiplication. So we'll do A times B like that. And I want that to be rational. So it's going to be contained in the rational numbers. This would be how I'd express that statement. For all A and B contained in Q, A times B is contained in Q. In this case, I used a comma here. In fact, probably the main difference to know whether to use a comma to separate the preamble with the statement here or a colon is whenever you use the word such that in a sentence, it's probably best to use the colon. In other cases, it may be best to use the comma. You can kind of interchange them as well. You don't have to use one or the other every time. Okay, so it turns out that combining two of these works pretty well, and the same works for exist as well. So if you want to do two exists in a row, you can actually just do exists and then do a comma here and then combine them. Same thing works for their exists. Okay, now the tricky part comes in when we have a combination of an existential quantifier and a universal quantifier. So it turns out that the existential and universal quantifiers are not what we call commutative. So it actually matters what order we do them in. So let me give an example of this. So let me write down a statement in symbols, and then we're going to go ahead and translate it into English. So here's that statement. So here's another example. For every x contained in the real numbers, there exists a y contained in the real numbers such that y cubed is equal to x. Okay, so let's parse this statement out right here. So what this is saying is for all real numbers, you can find a real number y such that y cubed is equal to x. So here this is written out in symbols. And what this is saying is that no matter what real number x you look at, there's going to be a matching y out there such that we can cube that y to get x. So based on your mathematical knowledge, is this a true statement? Can we find a y for every such x? Is that actually true? Yeah, that's right. Because we could do a cube root of any real number we want. So for example, let's say my x was equal to 8. Well, then in that case, there exists a y that will work for this. The y in question would be 2. And 8 isn't special. We could do this with any real number. And every real number has a cube root, which we are y right here. So this is a true statement. This is undeniably true. Now let's see what happens if we flip the order of this. So we put there exists the y first, and then for all of the x. Let's see how the content of this changes. So in this case, there exists a y in the real numbers for all x in the real numbers, such that y cubed is equal to x. So in terms of English, this is saying there is a real number y such that for any x in R, y cubed is equal to x. So it may seem at first like these are really the same statement here, but let's think a little bit more carefully. What this is saying is that we can pick a y out there. So we can pick a real number y such that no matter what x we choose, if we cube that y, we'll get x, no matter what the x is going to be. Is this statement true like this one was? Yeah, no, this one's actually not going to be true this time. So let's see an example. So let's say I pick my y to be 2, right? So let's say that this is the number that will work. So there is a y in R, maybe it's going to be 2, such that no matter what x we have, if we cube this particular y, we'll get any x. Well, this will work for one particular x. I guess this will work for x equals 8. Yeah, so that actually will work out. So, all right, so that's true. But will the same 2 work for x equals 9? No, because if we cube 2, we get 8, which is not equal to 9. And will this work for x equals 10? Will it work for x equals pi, for 0? No, it won't work for any of those. It doesn't work for all x. So this y equals 2 is not going to be it. So it turns out that no matter what real number we pick, the same thing will result. We can't just have a single number be the cubed root for all real numbers simultaneously. That's what this statement right here is saying. This is saying that there is a singular cubed root for all of the other real numbers out there. And that's definitely not true. All right, this distinction is crucial. Does anyone have any questions on the reason why these two are not the same? Okay. And to hammer this home, I'm going to give this in terms of a real life example. And I say real life loosely in that this happened in real life, but this isn't something that's likely to happen as you're walking down the street. Okay, so let's imagine for a moment that we are the TV personality Oprah, right? And how many of you are familiar with that TV episode where Oprah gave a car out to every single member of the audience? Does everyone, well, I don't know if you've seen that, but has everyone heard of that before? You should look it up on YouTube. She's saying like, oh, you could have a car, and you could have a car, and you could have a car, like that. So let's take a look at what the difference in the quantifiers would be for this particular situation. So what I'm going to do is I'm going to label a set C being the set of cars Oprah owns. And then I'm going to maybe make another set P to be the set of people in the audience. And then finally, I'm going to make a statement S of P. No, actually, I'm not going to do that. All right, so first of all, let's go ahead and see what this statement will be. So for every person in the audience, so for every little p in the big P right here, there exists a little c in the big C. So for every person in the audience here, there exists a car for them. And then on the other hand, we have that there exists a car in Oprah's collection for all of the people in the audience. So in that example where Oprah was literally giving a car to every single person in that TV audience, which one of these statements best symbolizes that? Is it the first one here, or is it the second one? Which one of these symbolizes what Oprah really did? That's right. Yeah, it's going to be the first one. So this is saying that, well, not quite saying, I would need to be a little bit more formal about this, but this is loosely saying at least that for every person in the audience, there is a car in Oprah's collection for them. So they each get their own individual car in this case. However, the next statement right here, let's think about what this will mean. So there is a car for all of the audience members. Now, in loose English, we can kind of imagine that these are saying the same thing, But let's try to imagine the ramifications of this scenario here. So if Oprah really played out what this is suggesting, then Oprah took a singular car and provided it to all of the audience members. So effectively, she wants the audience to turn into like a clown car situation where all the people get one singular car. So there's you can almost kind of put the word single here. So there's a single car for all of the audience members. And that's clearly not what happened, although that also would have been pretty memorable in all honesty. This is really what happened here. So for every single person in the audience, they're going to end up with their own individual car. This is a more kind of concrete example here. Right here. Isn't the backwards E at least one? Yeah, that's yet another equivalent phrase for there exists. So if we go back to the list here, there is or there exists. And depending on the context, you can say at least one, like that. Can you not say there exists at least one car for everyone in the audience for the second statement? So this is sort of the convention here. When you do the exists first, this is going to need to be the specific member of this set for all of these right here. So this specific little c right here is going to need to do it for all of the little p in here. Whereas when we read it this way, every single little p is going to get their own individual c right here. So that's the meaning of these two statements, and writing them in the reverse order flips which one we're talking about here. So let me kind of summarize. So if we have for all and then there exists, that means that, so for all s, there is, there exists a t, each member of S has its own individual member of T. That's really what this statement's saying right here. And then if we were to reverse this, there is a T for all S. This is saying that one particular T works for all members of S. So it's the same specific one, and at least one of them. So the same specific one works for all of them. All right. Oh, yeah. Oh, Vamshi, I guess I see what you're saying here. Yes. So this statement could also be construed as that there is at least a single car for all of the audience members, but this definitely isn't guaranteeing that all of them will get one. So this situation could still occur. Okay. Now, in the previous two examples where we did this right here, one of them was true and made sense, and then the other one was false or was a bit ridiculous here. Well, I guess this could conceivably happen, so I guess it's not totally out of the question. Yeah, yeah, I suppose so. But sometimes in mathematics, one of these really isn't any better than the other. Sometimes both of these statements are meaningful and useful. They just might not mean the same thing. I want to go over one instance of that as well. So I don't know if you saw this in calculus. We usually don't do this in Calc 1 here at UF, but maybe you took it somewhere else, or maybe you found this information on your own. So in Calculus 1, we're often concerned with taking limits, right? So in Calc 1, we have the limit as x approaches a of f of x equaling L. That might be a statement that we might write in Calculus 1. Now, it turns out there's actually a way to write down the definition of a limit in terms of existential and universal quantifiers. So this statement right here is equal to the statement for any epsilon, or for every epsilon greater than 0, there exists a delta greater than 0, with these both being real numbers, such that x minus a in absolute values being less than delta implies that absolute value of f of x minus L is less than epsilon right here. And I know a lot of you are considering either majoring in mathematics or at least minoring in mathematics. Somewhere along the line, you're likely to take a class called advanced calculus. This is where you talk about what the limit really means, like saying, oh, you get close enough to a particular number isn't good enough anymore. You need to be rigorous with what you're saying. And it turns out that the limit can actually be written in this way right here. So let's go ahead and parse this out right here. So the limit as x approaches a of f of x equals a particular number L. So what this is saying here, let's go through the statement carefully, is that for any epsilon greater than 0, so for any real number, we should be able to find a particular delta for that epsilon. So each epsilon can have its own particular delta, such that if absolute value of x minus a is less than delta, then absolute value of f of x minus L is less than epsilon. Now, in mathematics, absolute values often represent distance. So this can also be thought of as the distance from x to a. So we're saying here that if the difference from x to a, or the difference of your inputs, is less than some small number delta, then that means that the difference of your outputs, so this is the distance from f of x to L, will also be small. So what we're doing is, let's use a concrete number here. So let's say that I want my difference between my function value and the limit to be less than 1/2. Then that means that I should be able to find a close enough distance that when my inputs are close enough that they're within that distance, maybe delta is like 1/4 or something. Maybe if my inputs are within 1/4 of each other, then my outputs will be within 1/2 of one another. And here's a famous kind of visualization of this right here. So let's say this is the point A, and then this is the value L, and then here is our function right here. So here's f of x. Let's say this is a minus delta, a plus delta. We have L minus epsilon, L plus epsilon. We kind of draw this sort of window right here. And what we're saying here is that if I want to be within epsilon of this L value here, so I want my y to be close to this L value, then that means I need to have an input that's at most delta away from this A. Because remember, delta represents the distance away from x right here. So what this is saying is that if this limit is true, then if I plug something in this region right here, like if I plug in an x value in this region, then I'm guaranteed to be within epsilon of my target right here. So this is the precise meaning of a limit. I can get as close to my y value as I want, provided I find a delta that's going to be small enough. I plug them in close enough to that point, then my output will be close enough. This is the more formal way of saying that. Okay, so that's the limit definition of the derivative. Now, don't worry, I'm not going to quiz you on this or do anything with this. I'm just using it as an example. So this is the limit definition of the derivative. Now, let's suppose that we flipped the order of these right here. So let's imagine what would happen if we flip the order. So here, now we're going to say there exists a delta greater than 0 for each epsilon greater than 0, such that, and then we have the same condition as before. So we're not flipping anything over here. We're only flipping the existential and universal quantifiers. All right, so now let's remember what this meant. So in this case, no matter what epsilon we picked, we can find a delta that worked for it. So this is like saying for every audience member, we can find a car for them. This one is being like, we're going to have a car, a singular car, for all of these audience members. All right, so let's reinterpret this statement now that we've flipped this right here. And it turns out that this will actually still mean something, but it won't be the same as a limit. It'll actually be something slightly different. All right, So let's imagine this here. So they're saying that there is a distance you can go such that for any epsilon here, so for any distance, you're saying that if you're within the delta, then you're automatically this close to your L in the outputs. Remember, this represents the input for your function, and this represents the output here. So this is saying that there's a single threshold for all of the epsilons, such that whenever you get within that threshold, you're less than any distance away from f of x here. So this is saying that once we get within that critical delta distance right here, let's say delta is like 1. Whenever we get within 1 of this a value right here, then that means that this absolute value will be less than any epsilon we want for all of them. Now let's think about this here. If you have an absolute value that's less than any positive number, because remember, it's going to work for all of them now. This is going to be less than any epsilon, then those are all positive. What does this absolute value have to be? That's right. So what this is saying, what this statement is saying, is that there is going to be a threshold delta such that when your input gets close enough within delta away from your particular value a, then this is going to be less than all positive numbers, implying that this is going to be 0. So we can actually just replace this with the absolute value being 0. Because if you're less than all of the positive numbers and you're an absolute value, then your only option is to be 0. Does that reasoning make sense? Does anyone have any questions on that part? Okay, feel free to speak up or type in the chat if you do. All right, now let's examine the implications of this further. So if we have the absolute value of the subtraction of two things equaling 0, what does that say about f of x and L? If absolute value of f of x minus L is going to be 0 for any x in this region. They are the same. Very good. So another way we could write this, based on this right here, is that f of x is equal to L. So this is really what our statement is saying this time. So there exists a delta greater than 0 such that for all epsilon greater than 0, you being within delta away from A means that f of x is equal to this particular value of L. Now, this may be a bit hard to type out. Maybe someone can verbally explain this. What will the picture look like for this statement right here? What will the picture have to look like for this statement to be true? Can anyone figure it out? And if you can type it, express it in writing, feel free to type it in the chat as well. Malik, yeah, you're onto something here. So this is saying, all right, so let's draw the picture here. Is it just continuous? No, this is actually closer to continuity here because continuity respects limits here. It's actually a bit stricter than continuous. I like Malik's idea. A straight line. What kind of straight line would the graph have to be? Horizontal. Very good. That's right. Because as long as we're close enough to this A, our f of x will have to be this specific number. It's going to be specifically equal to L. So the picture for this problem would maybe, a function that would work for that would be something like this. So what we're saying here, maybe this is our A. This is A minus delta, A plus delta. And then this is our L right here. So what we're saying is that as long as we get within a certain delta of our A right here, as long as we pick any x in here, our f of x will be equal to a certain value. So this L right here, it's going to be the same value all throughout this region. F of x will have to equal L right here. So that's actually what this statement is saying right here. So this is just another example that switching the order of these changes what you're saying mathematically. And this is the limit definition. This is the definition of the limit right here. This is expressing that f of x is what's known as locally constant at a. So this is used a bit less often than continuity in limits. This is saying that close to a, f of x is just viewed as a constant function. So if you're close enough to this point a, f of x will be constant. However, if you move far enough away, so if we keep going outside of this delta range, then this doesn't need to be true. So if we move outside of there. But if we're within this special little area right here, this function is going to act like a constant. So this is a more complicated example of showing what happens when we flip the order of these. All right. And then now in the last few minutes here, I want to get to sections 2.8 and 2.9. But those were essentially very short. So 2.8 had to do with conditional statements. And essentially what 2.8 is saying is that if we have two open sentences, let's say we have P of X implies Q of X right here. Like for example, I think the example the book used is that X is even implies X is a multiple of 6. Here's the example. So in this case, for open sentences, remember, the truth or falsehood of those open sentences depends on what X is. So let's say that X is equal to 6. So in that case, we would have 6 is even, that's true, and 6 is a multiple of 6, that's true. So then that means the implication is true as well. But we could also have something like X equals 4. We would have 4 is even, that's true. 4 is a multiple of 6, that's false. So we have T and F here, and then this would be false. So at its core right here, this at least looks like an open sentence. Because this, the truth value of this implication seems to depend on what X is. However, there's sort of an unwritten rule in mathematics that when you write out P of X implies Q of X, you really mean for all X in the set you're considering, P of X implies Q of X. So even if it's not explicitly said here, when you write out a statement like this, you really want it to be true for every X that you could plug in. So let me ask you a question in general. So is the statement X is even implies X is a multiple of 6 true? So what's the answer to this question? Is this going to be true? You're right, and the answer is no. And at first it might seem like, well, it depends on what X is, but according to this convention right here, in order for this implication to be true, it needs to work for literally every single X possible. So since it doesn't work for at least one of the X's, which is 4, then we would say no to this. So whenever you have what seems like an open sentence and you use an implication with those, it's supposed to work for any possibility of the open sentence. That's just a convention that we use in mathematics. We don't say for all X and X. Sometimes we just drop that. All right, and that's essentially what 2.8 is saying. That's the gist of what it is, and then just take a page to say that. And then 2.9 is essentially just more practice changing English into symbols right here. And so let's go over one example for that again, although we've essentially been doing this whole time. And also 2, right? Oh yeah, that's right. So if there's at least one of these this doesn't work for, then this statement's going to be false. But if X is odd, doesn't that make P false, which automatically makes the statement true? Well, all I'm doing is I'm establishing a convention here. I'm establishing the convention that when I say this, I'm really putting a, or any X in capital X right here. So what I'm really doing is I'm kind of just putting one of these in the front, because this statement technically as written is an open sentence, but this right here is actually just a statement. It's either true or false. It either works for all of these X's or there's one it doesn't. So for example, if we use Vamshi's example here and we plug in 2, that's going to make this statement not work. So we would say that X is even does not imply X is a multiple. And the X we're considering is the only even X's. No, in this context here, the context would probably be the integers for this. So for any X in the integers, X is even implies X is a multiple of 6. And that is a false statement because of the existence numbers like 2 or 4. So the moral of this is, and most people read this anyways, read it this way anyways. So if this seems kind of strange, like why are we bothering talking about this, then you already got the memo here and you're good to go. So pretty much just whenever we have implications here involving open sentences, there's really a secret for all right there. All right, and then 2.9, I'm actually not even going to go through this one. You could read the book here. It kind of just gives additional practice in writing out changing English into symbols and vice versa. There's not really a lot of new content in that section. There's just more explanations and additional practice. So we've already been doing that quite a bit today. All right, so that's about it for today's lesson. So tomorrow we're going to finish up chapter 2. We're going to finish up talking about logic, or at least the logic we're going to get to. And then we're finally going to get to the meat of the course, which is chapter 4, where we're going to begin learning how to prove statements and, more importantly, write up clear and concise proofs. So I'll see you all tomorrow when we do that. And if you have any questions, feel free to stick around and ask them, and I'll be able to help you out. I'm going to stop the recording.